UX. So it's great to be here. So just want to first explain why I'm going to talk about the things I'm going to talk about. So I prepared a survey that most of you, at least the students, filled out months ago. So I asked, which of these topics have you already learned? So there's a list of topics here, and then kind of various degrees of comfort with those topics. And then, so this is what your responses were. So at the left is never not learned this topic. On the right was kind of the most confidence. And so Bayesian inference, that's what I'm going to focus on this morning. So you see we're pretty broadly distributed here. And these two topics here, as I'll focus on today, these Markov chain Monte Carlo and something called variational inference, these are really our main practical tools for doing Bayesian inference. So the theme of my lecture this morning is being a practical Bayesian scientist, which means really understanding and using these techniques here. As you can see, variational inference, although really to be Bayesian, you really need to be equally aware of both of these and really pick the right tool for each job. But we're definitely asymmetric. In astronomy, we focus much more on Markov chain Monte Carlo. So I think for a lot of you, it'll be useful to learn and get the kind of the complementary perspective for this other approach, variational inference, just to kind of show you a bit more flesh out. So the other things we talked about, I asked you about were Gaussian processes, random forest, neural network fundamentals, and I think this one was deep learning architectures. So actually, in some of the some more supposedly advanced topics, it seems like a lot of you had good preparation. It was really more in the fundamentals where I think there was an opportunity to really really talk about some interesting new material for you. Okay, so today I'm going to be talking about practical Bayesian inference. All of the slides I'm going to show, it's actually a Jupyter notebook. There's a way you can build a normal Jupyter notebook and then actually present it as slides. That's what I'm doing here. But what that means is that there's a GitHub repository with this notebook, and all of the plots and numbers and examples are actually, they're actually live. There's all of the code to generate them is in the notebook itself. And as X mentioned, so for 2 years now, I've been teaching a course at UCI called Machine Learning and Statistics for Physicists. It's a grad course. It's actually one of our most popular grad courses at the moment. And so a lot of the examples that I'm going to show are drawn from that course. So. Okay, so I want to start just with a high-level introduction for some of you and a review for others of what being a Bayesian scientist means. And really the fundamental question that we need to start with is what do we mean by a probability? So at one extreme, we have a very kind of crisp definition, which is attributed to the frequentists, and that is that when we talk about a probability, what we're saying is we're measuring the likelihood of different outcomes for some uncertain but infinitely repeatable process. Okay, so it's something that's inherently uncertain, but if we want to, we can make an arbitrarily precise measurement of the probability just by pressing a button, and we'll just keep getting new random outcomes, and we just need to tabulate how often different outcomes occur and just calculate as a ratio the frequency. So for example, a classic example is if you have a coin. If I give you a coin, you can toss it as many times as you want to measure the probability of getting heads, for example, to arbitrary accuracy. Okay, so here's a statement, the kind of statement that we like to make as astronomers. For example, the age of the solar system is at least 4 gigayears. So I want you to discuss in pairs now, just for a few minutes, how might you assign a frequentist probability? Using this definition of probability, how might you assign a probability to this statement? Right? Are you confident? Are you confident at the 95% confidence level, for example? How would you actually, as a frequentist, measure that 95%? How would you defend that? Okay, so I want you to pair up. If you're sitting far away from someone, get up and move. First thing, before you start answering this question, just introduce yourselves so you know who you're talking to. Okay, so over to you. Okay, so let's talk about this. So first of all, just what's your sense? Is this something that's easy or hard to do as a frequentist? What's an example? I mean, how might you approach this? Shout out some ideas. What could you do? You need something that we can repeat, and when we're just going to tabulate how often we get more or less than 4 gigayears, and that's how we'll get our probability. So what thing can we repeat that informs us about the age of the solar system? Any ideas? Yeah?
If we have like some hypothesis we could forward model, we could say, okay, if our model will produce some data that we get some summary statistics from, we could do that a bunch of times and see how different those statistics are from the one set that we really measure. So hypothesis testing.
So you'd have a simulation then of the.
Yeah, or even that might overcomplicate it, but even just some way of saying what do we expect to see under each hypothesis. It might just be an equation.
Okay, but there's not really physical outcome that you're using there. You understand that's a way of kind of getting something repeatable, but it's not really the thing that's repeatable there is not really directly measuring the age of the solar system.
But you'd compare whatever you measured from that to your one, not repeatable.
Yeah. So there is a fundamental problem here, if we want to be a frequentist about this. How many solar systems do we have? Okay, we only have one, and we only have one solar system at this present moment where we can make a statement like this. Okay, so this definition of a probability is it really boxes you in. It's really narrow. Okay, so a Bayesian takes the opposite extreme and says that you can assign a probability to any statement. Okay, so that statement there is no problem. But what you give up with that freedom is that it means that you're automatically going to have to put in some subjective input, except when you really can just count frequencies with some just by pushing a button a large number of times. So when we decide what we mean by probability, we have to pick there's a spectrum, and the two extremes of that spectrum basically are a frequentist, an extreme frequentist position allows us to make statements objective statements about the probabilities of uninteresting things, right? Whether a coin is fair, relatively uninteresting, or you can make subjective statements about the probabilities of more interesting statements, like is the solar system at least 4 billion years old? So but it is a continuum. Most people aren't really at one extreme or the other, and a really important thing to remember when you hear people getting kind of ideological about this is that in practice, any sensible methodology anywhere on this spectrum is going to give you consistent answers as long as you have sufficiently informative data. Okay? None of this ideology really matters if you've got good data. Okay, so you have to start by just deciding what you allow as a probability. But whatever decision you make, you're going to have, if you have probabilities of two different things, call them A and B, and if you have a background in probability theory, so A and B could either be random variables or just any logical proposition about possible outcomes. So it doesn't really matter exactly what we mean by A and B, but we've assigned each of them a probability. And then we have this concept of, well, what's the probability of both of those outcomes occurring? So kind of to think in terms of set theory, it's just the intersection between the set of outcomes A and the set of outcomes B. And then we just have, we can define these ratios where we have the intersection in the numerator in both cases, and we just put the different probabilities in the denominator. And that is a definition of what we mean by conditional probability. Okay, nothing controversial about that. There's quite a lot of different ways to formulate a theory of probability. In some approaches, these are axioms of the formulation, and others, they basically follow directly from the axioms. So this is just defining a type of probability, a conditional probability, the probability of A given B, or the probability of B given A. And you can do this, whatever you allow as a probability. And then Bayes' rule, which is the foundation of Bayesian statistics, is just a consequence of this definition, right? If we just cancel out the intersection, the probability of A and B, we get this thing here. Okay, so it's just algebra from this definition. So Bayes' rule itself is entirely non-controversial. Okay, if you accept probability as a self-consistent theory, then you have Bayes' rule. So really the controversy is, what are you going to accept as a probability? Okay, so Bayesian statistics, we start with a particular joint probability. So there's a probability of observing some data, D, of having some model parameters, theta, and assuming some hyperparameters, hyperparameters m. And so the reason I put a subscript on the model parameters here is just to remind you that in general, the model here, m refers to your choice of model. And if you choose a different model, like I'm going to fit this thing with a single Gaussian or a double Gaussian, that changes the parameters. The double Gaussian requires more parameters. Okay, so really the appropriate parameters are going to depend on the choice of hyperparameters, or colloquially the model. So I want you to now discuss what is the practical difference between a parameter and a hyperparameter. Why am I making a distinction between these things here, thetas and the m's? And to be concrete, I want you to give an example of both a parameter and a hyperparameter for a simple neural network like the ones that Shirley was talking about. Okay, so just to take a few minutes to discuss that. Parameter versus hyperparameter, and give examples in a neural network. Okay, so parameter versus hyperparameter. What's the practical difference? What do we mean by hyperparameter? What's hyper about it? Okay, maybe it'll help if we look at a specific example. Let's look at the neural network. So this is just a feed-forward, fully connected neural network. So the data comes in on the left. So that's where our data fits in. And now, this network is described by some parameters and some hyperparameters. So anyone want to guess what a parameter would be of the neural network? A weight, yeah. So a weight's, each of these links is associated with a real number. So the weights are parameters. Also the biases. So what might be a hyperparameter? Well, loss function is a function. So these are hyperparameters are still numbers. The number of layers? What is it? Yeah, number of nodes, right? So we could add another node here. I think someone said number of layers, right? So we can insert a whole nother. Yeah, well, it doesn't have to be fully connected. Okay. Okay, so in the context of a neural network, the hyperparameters are the things that govern the architecture of the network. But let's not focus on neural networks. More generally, what's the difference between the hyperparameters and the parameters? Think about their relationship to the data.
Parameter is something that is learned from the data, but an hyperparameter is something that you input by hand.
Right, exactly, right. So that is the practical difference, is a parameter is something that you're going to learn from the data, and a hyperparameter is something that you're going to externally impose, okay? So in fact, there's no reason why you couldn't learn the right number, the optimal number of nodes, or the number of layers. So that is possible, and there has been efforts to do that, although it doesn't work very well. But that's really the distinction we're making. And another kind of practical way of thinking about it is when you call like a scikit-learn function, right? So first thing you're going to do, let's say you're going to do a PCA. So first thing you're going to do is you will instantiate, you'll create the PCA object, and you'll tell it the number of components that you want. Okay? So basically anything that goes into that constructor, those are hyperparameters, because they're things that you're picking, and you're telling it, use this value. Okay, and then the things that when you call fit on your scikit-learn object, then the things that it's going to calculate, those are the parameters. Okay, so the joint probability has all the information, but what we do in Bayesian inference is that we actually use variations on the joint probability. We're interested in evaluating this thing here on the left, which is a conditional. So it's the probability of the parameters, what we can learn, given the data and given the model. Okay, so the model or our hyperparameters appears on the right-hand side because we're fixing them for this inference. And so this is just Bayes' theorem right here. I'm just using I'm putting theta on the left-hand side here, and then theta on the right-hand side. So data and theta are swapping places here. Okay, so that's how we can tell. It's just Bayes' theorem. It looks a bit more complicated because I'm also putting in the hyperparameters. And often when you see this written, you don't see the hyperparameters put in there explicitly. But it's important to remember that you always are assuming a model, whether it's the architecture of your neural network or it's the parameters to your scikit-learn constructor. Okay, so there's some jargon. We have names for each of these pieces here when we talk about learning parameters from data. So the thing on the left is what we call the posterior. This first term in the numerator, that's the likelihood. So if we read this, it's the probability of the data given some assumed fixed set of parameters and assuming a model. And this thing here is something that frequentists are also entirely happy to calculate. In practice, it really is something that's well-defined kind of at the frequentist extreme. Here, we have a weird object. It's the probability of the parameters given the model. So we can't directly observe parameters. So this definitely is no way that can have a frequentist, that probability can have a frequentist way of being computed. So that's really where all the subjectivity is going to be. And then we have this thing in the denominator, which is usually called the evidence. So we read this as the probability of the data given the model. Remember, our joint probability had three things: data, parameters, and hyperparameters. The parameters don't appear here, so that means that they've been marginalized out. Okay, so there's an integral. They've been integrated out. Some other jargon here. So we have different types of probability. A fully joint probability is when you only have commas in the expression. Okay, so this is the fully joint probability because there's only commas. A conditional probability is when you have the vertical line. And then a marginal probability is when you have something missing. Like here, we're missing theta. So this is both conditional and marginal. Also, there's a lot of jargon here, but we also have the statisticians and the machine learning communities use different jargon. So we think about our data, but in machine learning, that's often called just the features. Or if we think of our data just as a big spreadsheet, so the features would be the columns, and then the rows would be our individual samples or observations. We usually think of the things that we'd like to learn as the parameters. Those are often called the latent variables in machine learning. And then we have the hyperparameters, which is really the ensemble of hyperparameters is what's defining our assumptions about the model that we're going to try and use to learn about the data. So if you start reading theory papers in machine learning, they can be really heavy on probability calculus. So I think and you can easily get lost in that and put off by that. So here I have a link, just kind of a practical primer on being able to read these expressions and figure out what's conditional, what's joint, but also just like there's really just a set of three rules that you need in order to be able to do probability calculus. It's much easier than normal calculus. So that link will give you some more details on that. Okay, so the way I like to think about Bayes' rule is it tells us how to learn from data. So Bayes' rule here, represented by these arrows, it basically it takes two things. It takes our prior knowledge, the prior here, and it takes the new information, that's the data that we've observed. So these are the objects, the mathematical probability densities that represent those things. And Bayes' rule tells us how to combine those in an optimal way to update our knowledge. So we have what we knew before, and Bayes' rule tells us what we know now, taking into account the new information we've gotten. So that's how I kind of think of Bayes' rule. And notice there's an implied timeline. This is kind of yesterday, and this is today. And so that timeline is where we get this terminology of posterior, like later, and prior, earlier. Although there's really nothing special about the ordering of time here. So it's fine. There's no requirement that your prior data was actually collected before the data that you're considering new here. It's just kind of terminology. Okay, so now suppose you have a catalog. Someone's given you a catalog of 1,000 sources, and you believe that some of these are some new exciting class of object, right? These are going to be named after you. But you need a very expensive follow-up in order to confirm each source. So if you had an infinite budget, you'd just follow them all up, and you'd have a satisfyingly frequentist problem. Right? You want to know that in this catalog of 1,000 sources, You want to know how many of them. What's the abundance of this of the new object that's going to be named after you? And with 1,000 sources, that's really just a frequentist problem. Okay, but if you don't have an infinite budget, you're going to have to squeeze as much information as you can out of each follow-up you do. So let's take the extreme. Let's say you can only afford this year to do a single follow-up. Okay, so you're just going to pick one of these 1,000, and you're just going to get a single follow-up on it. So what could you learn about the abundance of your new, your hypothetical, exciting new type of object from this single follow-up? So you're either your follow-up is going to tell you that it is or it isn't this new class of object. So this is, Bayesian statistics is really is designed to solve this kind of problem where you really have limited information, and it's essential that you sensibly incorporate what you already know with a relatively limited amount of new information. And interestingly, in the history of Bayesian methods, for a long time, Bayesian methods were really shunned by academic statisticians. In particular, Fisher, who gave us Fisher matrices and Fisher information, was very against Bayesian methods. So a lot of the pioneers in Bayesian statistics were people outside of academic communities, but who were actually facing real-world problems. So they either kind of problems in military espionage, or industry, or insurance, things where there was actually lives or real money at stake. Those were the people that did a lot of the pioneering work on Bayesian statistics. And so this is a link here. There's a nice book that kind of covers all of that history. Okay, so let's be a little bit more quantitative here. So this is an example of if we just had the infinite budget and we just followed up all 1,000 of our objects. As I mentioned, so this is really a Jupyter notebook. So this piece of code, if you download the notebook, you can execute all this. There's some hidden cells, like defining this Bayes learn. But when you execute this one, then it will produce this plot here. So this here, we've followed up 1,000 of our objects, and we've found that 200 of them are of our exciting new class. So that's great. You're going to get this object named after you. In this case here, the prior we assumed is flat, so that you can see why it's called flat. That's a graph of a plot of the prior, the blue line here. But what flat really means is that the likelihood and the posterior. Okay, the likelihood is the thing on the right-hand side in the numerator, and the posterior is the thing we want to learn on the left. So they're identical. So the dotted line and the orange curves are the same. So in the expensive approach, you get a very sensible answer, right? You followed up 1,000 objects, 200 of them were interesting, and you have so your estimate of the abundance is 20% with some uncertainty that's quantified by the width of that. Okay, but we don't need Bayesian statistics if we can get such good data. Any sensible method, I said earlier, is going to give you the same answer. So, but what if we can only afford to do one follow-up? So we have one follow-up, and then let's say that it turns out not to be this new class of object. So with a flat prior, we're still going to have that the likelihood and the posterior are the same. So the posterior looks like the likelihood looks like this for the model I took. So that's also the posterior. Okay, so but that's one possible outcome. And the other possible outcome is that we observe an object, and it is the interesting type. Okay, so now this is telling us that the most probable abundance is 100%. But we know that this is some class of object that's never been seen before. Okay, we have some sort of bias that it is a rare object, right? No one's going to believe us if we say we found this object and it's 100%. Every object we've been looking at is this thing. Okay, that's ridiculous, and that's because we're not really we're being lazy, and we're not thinking carefully about what our assumptions are. What is our prior knowledge about this? And so the laziness is in this choice of a flat prior. Okay, so. Although this seems like a very straightforward, nice frequentist, defensible, objective approach, is clearly giving us answers that we don't believe. Okay, so being a rigorous Bayesian forces us to assign some prior belief. So here, for example, I'm saying this blue curve represents my prior belief. And now, because this isn't flat, the likelihood hasn't changed. Okay, but when we multiply those two together, we get a posterior like this. So notice how the posterior, the blue curve, is only a little bit different from the original curve. Okay, and that's because our measurement, in this case here, we didn't observe it, and that's pretty much consistent with our prior belief that this thing is rare. And so, we have a result that's very influenced by our choice of prior, and that's because our data isn't very informative. We've only made one observation. But that's life, right? If you have crappy data, then you're not learning very much. And so think of that flow, right? We have what we knew before. We add some data, which isn't really worth much here. And so what we end up with is pretty much what we knew before. Okay? And that you can see that. So Bayesian inference is a way of formalizing, writing down what we believe, and then propagating it through to say what we've learned. So this is if our follow-up didn't find it, but if we do find it with our follow-up, we get quite a different answer. Okay? So sure, this requires some subjective input. We have to commit to what we really believe before we look at our data. Okay, and it's really important that you write that down before you look at the data. You can't be influenced by whether this follow-up was positive or negative. And then we get quite a different answer. Okay. But at least it's giving us some sensible results. So one test would be, well, if we've observed one, if we're 1 for 1, okay, we don't know what the abundance is, but we know it can't be 0. We've got one of these things, so it can't be 0. And notice, so the Bayesian approach does tell us, well, the one thing we're sure about is that it's not 0. Okay, so it's doing sensible things there. But still, we really don't have good data, and so if you were to change your blue curve here, your prior assumption, it is definitely going to change this. That's life. Okay, so why is this hard to do? Okay, it just kind of boils down to this simple ratio of probabilities. We just need to have 3 things here. In fact, we really only need to calculate one thing, the likelihood. We need to write down what our prior belief is. And then this third thing, in some sense, we get it for free, because since this is a probability on the left, then this thing on the right has to be a probability. So the fact that we know that this is normalized allows us to write down what this must be just as a normalization constant. So we're integrating over all possible parameters. So the theta means that this is kind of a free variable that's going over all possible parameters. And in the language of probability, notice how there's no theta here. So that means that this is a marginalized probability. And marginalization is just summing over all of the unobserved states of the variable that's missing, theta in this case here. Okay, so we kind of get this last thing for 3. So there's only really 2 things that we need to do this Bayesian calculation. But this thing here, this integral, is generally really hard to do. And that's what makes Bayesian inference hard. So there are some rare cases when you can just calculate the normalization with brute force, or maybe with some analytic finesse. But in most cases, you're going to have to use an approximate method. Okay? And fortunately, though, there are 2 really good options for doing this. So that's what I'm going to be focusing on this morning. So one of them is Markov chain Monte Carlo. That was invented in the 1950s, actually mostly by physicists trying to build better bombs, because that's where the money was after the war. And the other approach, though, which I guess less of you are familiar with, is variational inference. And that's much more recent. It was invented in the 1990s. So one nice thing about these 2 approaches is that the assumptions they make and the numerical algorithms that you use to solve them are fundamentally different. So in Markov chain Monte Carlo, it's basically sampling. It's generating samples from a random distribution. In variational inference, it's mostly optimization. Okay? So finding the maximum or the minimum of some of some complicated function. So very different kind of complementary sets of numerical tools. And that's good because that means you get different trade-offs between these methods. So depending on your problem, there'll be one or the other which is better. So that's why it's important to know about both of these so you can choose the right method for your problem. And then there's a fourth scenario which is less good, but which I'll also mention briefly, something called Laplace's method. So what's nice is that it's pretty easy, but the problem is it only gives you partial results. So. Okay, so just briefly, so when can you do Bayesian inference exactly? So when all of the parameters have just a finite set of discrete values, so you can actually just enumerate, you can write down on a piece of paper what all of the different possible outcomes are. Okay, so you have no continuous parameters. Then that evidence integral just becomes a sum, and you can calculate the posterior exactly, at least in principle. Often in practice for interesting problems, the number of discrete states, the number of terms in that sum can be prohibitively large because you have a kind of a combinatorial blow-up. But at least in principle, you can do it exactly. But how often do we really not have any continuous parameters that we're interested in? That's pretty rare. So when you do have continuous parameters, you have to do some integration. But there are certain combinations of a likelihood and a prior function, those two things in the numerator for a Bayes rule, which give an evidence integral, the thing in the denominator, which you can actually do analytically. Okay, there are some hard integrals that you can actually do analytically. And then in a subset of those, some really special cases, the posterior that you get out, sitting on the left side, has actually the same functional form. It's from the same family of functions as the prior. And in that case, we say that, so that's a special combination of prior and likelihood, and we say that they're conjugate in that case. So there aren't very many cases, examples of conjugate, prior, and likelihood, but it turns out that there's some really important ones in the small set that exist. They're all listed on a Wikipedia page here, I put the link to, but that list, if you look, includes, so if you have a Gaussian likelihood and a Gaussian prior, okay, so basically, if you take the integral of a Gaussian times a Gaussian, you're just going to get another Gaussian. So that means your posterior is also Gaussian. Less obvious is if you have a Poisson, so if you're counting small numbers of photons, for example, so you have a Poisson likelihood, then if the gamma distribution is a good choice of prior, that's really nice. You can do the integral analytically, and the posterior will also be a gamma function, just with a different parameter. Okay? The gamma function has one parameter, so you'll put one parameter in for the prior, and then you can just, without doing any integration, you can just calculate with algebra what the corresponding gamma parameter will be for the posterior. For discrete problems, if you just have a kind of coin toss, two-state possibility, so you would describe the likelihood with a Bernoulli distribution. If you have a beta prior, then your posterior will also be beta. If you have multiple categories, we're trying to classify galaxies into red, green, blue, whatever. You can tell I don't do galaxy physics. Then that will be a categorical likelihood. If you have a Dirichlet prior, a particular class of functions, then your posterior will also be a Dirichlet. Okay, so this doesn't happen very often when this works, but when it does work, you should obviously do this. You have no computation to do at all. It's lovely. So you should know about this. Okay, that method which I said is not so good is Laplace's method. So the idea here is pretty simple. So we find a point in the parameter space which maximizes the posterior. And the nice thing, so this is an optimization problem. But the nice thing about optimization is that we don't care how things are normalized, right? The thing that's hard, this is not the posterior because it's missing the normalizing constant down here, the evidence. But if we're going to find the maximum of this surface here, it's the same as the maximum of this surface here, right? Changing normalization isn't going to change the location of the maximum. So we can find an optimal point in the parameter space without ever normalizing this thing properly. But what that gives you, it gives you what we call a point estimate, or the maximum a posteriori point in the parameter space. In fact, it's very unlikely that you will actually get the global maximum because although optimization techniques work really well, and they're getting even better with our machine learning toolkit, things like TensorFlow and PyTorch, although it works really well, you will almost always converge to a local optimum, not to a global optimum. Okay, so for a lot of problems, this is fine. If we've got an image and we want to classify it as a cat or a dog, then we really just need a point estimate. We just want an answer. But for doing science, that's never enough. We need to know the uncertainty. If we're going to say it's a cat, what's our confidence in calling this thing a cat? So just solving this optimization problem doesn't tell us anything about the uncertainty. So the idea of Laplace's method, though, is to get kind of a first-order handle on what the uncertainty is. And so the way we do that is that we assume that the posterior is Gaussian. Okay? So we're assuming that it's Gaussian, and then we're going to make a Gaussian, and then we will, once you've made that assumption, the Gaussian is something, even in multi-dimensions, that you can analytically, we have an indelible neural network now. So the Gaussian is something we can analytically normalize. Okay, thanks. So we have the true posterior is something like that. And with optimization, we can find the point theta 0 where this reaches our maximum. And then what we're going to do is we're going to say, well, I'm just going to assume that I don't know what this shape is. I'm just going to assume that it is a Gaussian. And I'm going to say that that Gaussian is centered at the maximum. And now I'm going to just find. I still haven't said what the width of the Gaussian is, or more generally in multidimensions, the covariance. But now I'm just going to use my data to estimate the covariance of this thing. So effectively, I'm just fitting a Gaussian in the neighborhood of this point right here. And in practice, what you do is you calculate numerical second partial derivatives to build this thing called the Hessian matrix. So it's really just looking at the slopes. The first derivative is 0 because we're at a maximum, but we look at the second derivatives, and that will give us directly an estimate of the covariance. Okay. And you can always do that because at a Taylor series expansion, we're at the maximum, so there's no first derivative term. Here's our constant, and then the next thing is just covariance is the Hessian matrix here. However, whether this is useful or not really depends on how quickly the true posterior distribution diverges from our assumed Gaussian. Okay, this always works, whether or not the Gaussian is a good description or not. And so over what scale do we really want this to be true? In this example here, would you say the Gaussian is a good approximation? It kind of depends on what questions you want to answer. I would say in general this is not a good approximation because it pretty quickly diverges. But the relevant scale, like if you want to make statements about 95% of your data, that means that they need to agree, going out to several sigma, right? So that in that case, it's clearly wrong. If you really only cared about the 5% most probable, then maybe you'd be okay there. But that's pretty unusual that you'd be so focused just on the small most probable subset. So in general, although the Taylor expansion guarantees that it's fine when you get close enough to your best parameters, in practice you want it to be a good fit out to several sigma, and you have no way of knowing whether that's true without doing the much harder job of figuring out the full shape. And at that point, now you're then doing MCMC or variational inference. Okay, so unless you happen to be in the happy place where you can really do things, just enumerate a completely finite parameter space, or else you have conjugate prior and likelihood, so you can do things fully analytically. So then we need some sort of numerical approach. Okay, so the two that I mentioned at the beginning are Markov chain Monte Carlo and variational inference. So now we're going to dig in a little deeper and talk about each of those. So how many of you have ever run a Markov chain Monte Carlo? Forget, maybe nothing Bayesian, just to look at some chains, some Planck chains or something like that. Okay, so about half of you have some practical experience of Markov chain Monte Carlo, but you might not have thought about it as a key tool for Bayesians. Okay, so I just want to give you a quick bit about the formalism and how does Markov chain Monte Carlo kind of fit into our theory of stochastic processes. So a stochastic process is just some black box which spits out numbers. Okay? It has a button on it. Every time you press a button, it spits out another number. So you get these chains of numbers, or just random sequences coming out. And in the most general stochastic process, each number that comes out depends on all of the other ones that came before. So there's an arbitrarily complex internal state to this black box. Or we could say that it has long-term memory. It remembers everything it's done in all of the previous button presses. So when we say a Markov chain, that's just a special case. It's a subset of a general stochastic process where each number that comes out only depends directly on the one just before. Okay, so we're building, we're ripping out almost all of the memory from our black box, and it only has a very short-term memory. It can only remember the last number that it gave you. That's what we mean by a Markov chain. And then a stationary Markov chain is even more specialized, and that is that it uses the same rule. Every time you press the button, it uses exactly the same rule to take the last number and turn it into the next number. So we can think of that as basically a black box that has short-term memory, but it also has no sense of time. So it doesn't know how many times you've pressed the button. It does the same thing to get the first number as the 10th number as the 100th number. Okay, the rule doesn't change with time. So that's a stationary Markov chain. And stationary Markov chains are really the backbone of this MCMC technique. So in practice, a stationary Markov chain is going to be fully specified if I tell you two things. And each of those two things, you can think of as rules, but those rules can be boiled down to just a probability density. So I need a rule to generate the initial value. Okay, the very first time I fire up this block, I plug it in, there's some rule that's going to tell me what the first number that it spits out is. So it's going to sample it from some distribution here, p of x0. And then I also need a rule that will generate the next value from the previous value. Okay? And this rule doesn't change when the little n changes. That's what I mean by it has no sense of time. So this fully specifies a stationary Markov chain. There's another attribute of a Markov chain, which is reversible, which means that it actually has the same rule going in either direction. A reversible Markov chain is always stationary, but in fact not vice versa. But we don't have to use reversible chains. So that's just a special case. Okay, so when you have one of these stationary Markov chains that just governed by these two rules, a curious thing happens when you run it for a while. What you'll notice is that eventually it samples from some equilibrium distribution. So you take any stationary Markov chain, if it has a label on it saying stationary, then what that tells you is that after you've pressed the button many times, at some point, after some number of button presses, you are basically generating random numbers from some fixed distribution. That's what I call p of tilde. So there's some equilibrium distribution. So that's not at all obvious. So let me show you with a practical demonstration here. So I'm going to define a stationary Markov chain. So I need two rules. So I'm going to say that the initial value is chosen uniformly between 0 and 1. Here's the actual code for this. So it's a stationary Markov. It's a type of stochastic process. So for the initial, I'm just going to generate a uniform number. So my other rule is that in order to get the next value from the previous value, x minus 1, I'm going to evaluate this crazy thing here, okay? And I just made up some messy looking thing. It's got mods, absolute values, cosines. This is where the randomness comes in. We add 0.1 of a unit, of a number drawn from a unit Gaussian. So this is what it looks like in code. We've got the mod, the cosine, the abs. This is where the random number, the normal random number, comes from. So I mean, I deliberately not using some special functions, Poisson, because there's no tricks here. I mean, whatever rules we pick, we will always get to some equilibrium. Okay, so if you don't believe that, you can go in and edit, come up, change this rule, and you'll see that you'll still get into equilibrium. Okay, what do I mean by equilibrium? So I think the easiest way to see it is visually. So here, x0 is the very first number. So when you first plug it in and you press a button, so we're generating uniformly a number between 0 and 1. And then given the value of x0 that we got, the next time we press the button, we get x1. So this is showing you where it's bright. That means the probability of getting that combination of the first number and the 0th number and the first number. So it's basically, you can see the cosine here, the absolute value is giving us that, or the mod is making it repeat. So you can kind of understand this from the equation, but the details don't matter. This is just sort of a messy thing. So this plot here, this already encapsulates the second rule. Everything about the second rule is visualized here, because this shows you the probability of getting x1 given x0. And because it's stationary, that's the same thing as the probability of getting x10 given x9, or x100 given x of 99. Okay? So that image right here of the conditional probability of the next one given the previous one fully encapsulates the second rule. Okay, so what the next panels show you is it's always on the vertical axis is always the very first one to come out, x0, x0, x0. And then here we're getting the x1, second time you press the button, x2, x3, and x8. And what you notice is as you keep applying the same rule, which is represented here, then things become more and more uniform, and all of this crazy cosine stuff here gets completely erased. And by the time you've pressed the button 9 times, it's just vertical stripes. And what that means, the fact that it's completely vertical, means that it doesn't matter what your initial value was, right? The probability of getting x8 given x0, it actually doesn't depend on x0. So that is the visual signature of getting to equilibrium. Okay, if you prefer to think more mathematically than visually, you can think of this as a matrix, and each time you apply the rule, it's like multiplying this matrix by itself. So this is like the square, the cube, to the 8th power, and so eventually you're getting to you get to an equilibrium where it doesn't actually matter. So after you press the button 9 times, it has no memory of what the initial value was. Okay, so, and after this, 10, 11, 12, they're all going to look identical to this. So that means at this point here, every time you press the button, we're just sampling from this distribution. Draw a slice through here. So this most probable is down here, and then it kind of tails off, and then it starts to pick up again here. So we've got, our stationary Markov chain eventually just becomes a nice, well-defined random number generator, sampling from this thing here that I called p tilde. Okay, so how do we turn this into something practical? So there's 2 issues that we have to deal with. The first one is that we have no way of knowing in advance how big we need n to be to achieve equilibrium. So in that example there, because it's just a one-dimensional, the output is just one-dimensional, it achieves equilibrium pretty quickly. But in more complex examples, right, if you can often use these things where you're sampling in hundreds or even millions of dimensions, and then you really have no idea how many times you're going to have to press the button until you've really reached this equilibrium, and you're always sampling from the same distribution. And the other practical problem is that it's easy to create a stationary Markov chain by just writing down the 2 rules, the initial distribution and the update distribution. But really what we'd like to be able to do is we'd like to be able to do it the other way around. We'd like to be able to specify the equilibrium distribution, and then we'd like to have a chain that will sample from that distribution eventually, okay? It's not very helpful to write down the two rules because you don't know what distribution it's going to be sampling from. So it gives you it samples some distribution, but you don't really have any control over it. Okay, so that really requires solving an inverse problem, which is generally challenging. And so really the discovery in this field was that there are some general methods that you can do to say I want to build a Markov chain that will sample from a certain probability distribution. And there's actually kind of a family tree of them. So the most general algorithm is something called Metropolis-Hastings-Green. You've probably never heard about that because it's too general. It's not really that useful, the generality. And so kind of a subset of that is just Metropolis-Hastings. That's what I'll focus on because that has all the essential ideas. But then there are some special cases under Metropolis-Hastings. So Metropolis approach, the Gibbs approach, and then the Hamiltonian approach, which I won't have time to go into any details today, but it's if hearing Hamiltonian gives you, bad memories of your grad classical mechanics class, it's the same Hamiltonian, and it's actually a very physics-inspired approach to doing Monte Carlo. Okay, so I want to focus just as a general approach, way we can approach this on this Metropolis-Hastings algorithm. So the way the Metropolis-Hastings algorithm works is that we bring in some new distribution. Okay, we already have this thing that we want to sample from, and now we're trying to figure out, well, how do I make my initial distribution and my update rule so that this will be my equilibrium? And so to do that, I'm going to invent some new distribution called the proposal distribution. And you pick a proposal distribution that you can sample from easily. Okay? If you knew how to sample from your target distribution easily, you'd be done. You wouldn't even need to be doing Markov chain Monte Carlo. Okay? So we're going to pick some Q that we know how to sample from easily. In practice, that we almost always use just a multivariate Gaussian because it is very easy and efficient to sample from. But keep in mind that there's nothing magic about the Gaussian. I mean, any distribution that you know how to sample from, you can use for your proposal. Even crazy distributions. You can just have a uniform distribution or anything you want. But in practice, if you choose a Q that's in some sense closer to the target distribution, then you're generally going to reach your desired equilibrium faster. Remember, we don't really have any guarantees about how long it'll take before you get to equilibrium anyway. So, okay, so how do we use this proposal distribution? So there's two approaches, both are fine. You can either say that when we get a sample from the proposal distribution, we'll use that to just update. So we'll take whatever the last sample was and we'll add our sample from Q to it. Or else we can actually just take the samples from Q directly and say that's our next point. So it's really just a question of whether we're going to anchor always at the origin or some fixed point, or whether we'll just kind of anchor from the last point. And in this case here, it's pretty more common, anchoring from the last point, that's equivalent to a random walk. Okay, where it's a random walk where the steps are sampled from our proposal distribution. Okay, so we have two distributions. The one that we'd like to sample, P tilde, and our proposal distribution that we're using to try and make this job easier. And what we need to do is each time we're going to pick some sample from Q, and then that's our proposal. Are we going to accept it or not? Well, we calculate this thing here called the Hastings ratio. So it's just a ratio of the target distributions at the new step and the last step, and then a similar ratio of for the proposal distribution. The key here, and the whole reason why Markov chain Monte Carlo is so useful for Bayesian inference, is because we have a ratio here. Remember, the thing that makes Bayesian inference hard is that denominator, the evidence. But the evidence is just a constant. It's just a normalization constant. So it's going to cancel in that ratio. So that means that we can calculate this Hastings update, which is the key to doing, to getting a chain that samples the distribution we want, without ever needing to know that normalization. Okay, however, we still do need to be able to calculate this ratio. So that means we need to be able to calculate unnormalized values of the target distribution. Okay, so if you think about what possible values, I mean, this is just a number, and it's a number that has to be greater than or equal to 0, but otherwise it can be arbitrarily large, right? Ratios of probabilities will always be positive or non-negative, but they're not bounded by 1 or anything. And so the way this algorithm works is that when this ratio here is greater than or equal to 1, you're always going to take the proposed move. Okay, so you draw a sample from your Q. So you just generate a random number. And when this ratio here is greater than or equal to 1, you always will accept it. So you're always going to move to a new point in your parameter space. But what if it's not? Well, then you may or you may not. So you're actually going to have to generate another random number to decide whether to accept it. And you'll accept it with the probability. So if this is less than 1, that means it's between 0 and 1. And so we take that as a probability for accepting it. Okay? So kind of a visual way of thinking about this is you calculate the Hastings ratio. Okay, it's going to be greater than or equal to 0, but it's unbounded here. If it's greater than 1, we always accept it. So we have a 100% probability of accepting it. And then if it's less than, if it's between 0 and 1, then the probability of accepting it is just going to be linear in whatever the Hastings ratio was. Okay, so in practice, that's how we, that is a scheme that lets you start from a distribution that you want to be sampling and then figure out what the update rule is in order to do the sampling. The update rule is you pick something from your sampling, your proposal distribution, and then you decide whether or not to accept it with the scheme that I just described. Something that's not so obvious is sometimes you're going to propose a new set of parameters, and then you're going to decide, no, I'm not going to accept those, right? If it falls between 0 and 1, there's some chance that you're not going to accept it. What do you do in that case? Well, you stay at the same point. Okay, so that makes the parameters that come out of a Markov chain can have repetitions in them. In fact, it's very normal that they have repetitions in them. But that's not normally what we think of as a random sequence, right? Something where you have the same value repeated. That seems extremely unlikely. But that's a feature of a Markov chain, is you will get repetitions. Okay, so here is a concrete implementation of a Metropolis Hastings sampler. So again, it's a stochastic process. So we need to specify the initial value. So I'm just having it start at 0. And then the rule to update. So the update rule, what do? I take the last point. I'm going to add a sample from my Q distribution. And so that's my proposed move. And this here I'm assuming that Q is one of the distributions in the SciP stats class. So they all have this random variable sample or RVS method. Then I'm going to calculate the Hastings ratio here. And then I'm going to accept it. I'm either going to accept the new value or I'm going to stick with the old value. Okay, so that is a complete implementation for this. This is a stationary Markov chain that will sample from some target distribution. The target distribution is not hard-coded here. Okay, the way I tell it what distribution I want to sample from is I just pass in some function, log p, that calculates the log of p. So it's completely arbitrary. Any probability density, I just need to make a function that calculates the log of the probability density. And the reason for the log is just technically it just makes gives us a bigger dynamic range with finite precision floating point numbers. Okay, so I need to let's pick a specific target distribution. So here I'm just going to make a density that's flat inside a square. We'll say we have a 2-dimensional parameter space, and it's a uniform distribution, but in 2 dimensions. So it's going to be I want to uniformly sample a square. Okay, so log probability. It's fine to so the log of 0 is minus infinity, and it's fine to to work with that, and all of the math functions work fine with minus infinity. They know what to do. Okay, so this is a visualization of that chain. So just running the code that I just showed you with where I plug in the target distribution. So the dashed line here, that shows that's my unit square. So if this is working, I should be generating samples uniformly from this square. So I started it right here. That was the initial variable value. It's always in the center. The colors here indicate how far along we are in the chain. So the very first one is red, and then we get towards where the purples are later here. So you can kind of see it's really jumping around a lot. And in this case here, I'm using a very wide, my Gaussian is very wide. So a lot of the time, let's say if I'm here, a lot of the time I'm going to choose a proposed thing which is outside the square. So when it calculates a Hastings ratio, it's going to say, no, you can't accept that, right? So that's essentially going to clip it. It'll say we always reject it. But that means we're going to repeat that point. So the ones that have a plus in them, that means that it repeated that point once. So it occurred 2 times. The ones that have an asterisk in them, a little hard to see, so that's something that it stayed there 3 or more times. Okay, so you've got to be careful. When you look at this distribution, you need to remember that the statistical weight of things that have a plus or an asterisk in them is larger. And so what is the sense in which we've solved this problem by uniformly sampling? It's not that these points are uniformly filling it. It's that you need to remember there's a weight associated with each one of these points. So like this area here is kind of sparse, but then that one is at least 3 times, and that one's 2 times. So when you account for that, this is actually a lot more uniform than it looks. Okay? So if you're using Markov chain Monte Carlo, it's just a fact of life that you're going to get repeats. And so you should never assume that sample to sample they're independent. You can't get any less independent than just repeating the same sample. So we have solved the problem. We have uniformly covered this distribution. But there's 117 points that are repeated out of the 500. So this is a chain with 500 XY points, but only 180 of them are unique. Okay, so this is a solution, but it has some caveats. You've got to be careful if you're going to use that. This is another example. So in this case here, there's no pluses or asterisks, so no points here have ever been repeated. So that's good. We've solved the repeat problem, but we haven't really filled out the square very well. So does this mean, is this a counterexample that says Markov chain Monte Carlo doesn't work? I mean, you certainly wouldn't want to use those points there as a representation, as unbiased samples from the whole square. Okay, that would be bad. But remember I said that with Markov chain Monte Carlo, you don't know a priori how long you're going to have to run the chain for before you're really hitting the equilibrium distribution. Oh yeah, so right, so I mean, if we only ran it to here, right, well that would be bad, but then we could start one over here, and then we kind of have a lot of little worms filling this in. Yeah, that would be a fine approach, right? So there basically you would have an ensemble of samplers, and the only thing that would differ is their starting point. Yeah.
And eventually you could also, once you find what the convergence of a solution, just sample like the convergence region. So like you've got a local region around your global estimate of the best fit solution, and then just sampling that will let you be sampling across different distribution.
Mm-hmm. Yeah.
But how would you know to start within the unit square?
How do you know to start within this region?
Yeah.
Well, you let the chain converge.
How large? Another question is, how large region would you have to search to figure out that you should be starting?
That's a fair question.
So is there some sense in which this is actually doing the right thing? Yeah, just let it run long enough, right? So this is just a random walk. Eventually, it's going to fill in the whole thing, and Markov chain Monte Carlo does work. Once you let it fill in the whole thing, you really will have a uniform distribution over the square. Okay, so the reason we're not getting repeats here, in fact, we do have a few repeats right here, is because whenever you're on the inside, it's always, the proposal distribution is really tight. And so it's always taking it's proposing something which is still inside the box. So that's why we never get repeats. And except right here, when we're right on the edge, so then it did propose something that was outside the box that was stuck and had to repeat. So when we look at these simple two-dimensional examples, you can make a plot that tells you, well, that shows you clearly what the problems are. But remember, we often do this in 100 or 1,000,000 dimensions, and there you just can't make these plots. And so you just have to assume that these kind of things are going on, and you just have to use the samples you get from the chain intelligently. So. Okay, so let's do an example. So far there was nothing really Bayesian there. I was just telling you a recipe that if you're given some target distribution, how do I build a Markov chain that will sample from that distribution? Okay, so now let's put our Bayesian hats back on. So the distribution that we'd like to sample from is the posterior for some problem. So let's talk about a toy problem here. Well, not so toy, because we do this all the time. So we want to fit a straight line, okay, with two parameters, the slope and the offset, to data in 2 dimensions. So it has 2 features, x and y. Okay, so here's our, we can write down a log likelihood. Whether you're a frequentist or Bayesian, you'd write down the same log likelihood. So here's the data. We're summing over all the data. So we're assuming that the data points are independent from each other. So the log likelihoods just add. So we have the yi and xi. Those are each of our observations. Here are the unknown parameters, m and b. There's an uncertainty. The data have an uncertainty in y. I'm going to choose to fix that, which means I'm not going to try and learn it from the data. I could take another approach and learn it from the data, but since I'm fixing it, then that becomes a hyperparameter. So I have data x and y. I have parameters m and b, and I have hyperparameter sigma y. This messy thing here is just the normalization for the likelihood. So I generate some data to play with here. So you can see the error bars here show you that fixed sigma y. It's not varying with x. The dotted red line shows you the true answer. So that's the model that the data was generated from. It doesn't all lie on the line because of these uncertainties. Okay, so now I want to, so this is an example where we have somewhat limited data. This is not great data. You could draw a pretty wide range of lines through this. So it's not the extreme case where we've just done one follow-up, but it's not also the deluxe case where we've got thousands of points with tiny error bars. So this is the regime where Bayesian inference is really useful. So we need to, in order to generate a Markov chain, all we need is we just need to write down a function that calculates the log likelihood. Okay? And then I've already showed you just on one page, I showed you what it takes to sample from that. So there's really, you have a generic Markov chain sampler, and the only thing you need to plug in to tell it about the problem that you're trying to solve is the log likelihood, and the prior. So the log likelihood, so it's just written out here. It says 2 lines. We have the normalization piece, and then we have the sum over the data there. As I said before, the reason we're doing this log likelihood rather than this likelihood is just for numerical stability. Okay, then finally we generate some Markov chain samples of our posterior. And here I'm assuming uniform priors. So I'm assuming that both the slope and the offset have a flat distribution. Remember, flat just means that the likelihood and the posterior are going to be the same thing here. Okay, so MCMC, I feed it in my likelihood. That tells it what the problem is I'm interested in. And then I tell it the parameters that I want to infer, so m and b. And what this notation here means, you can look at the code in this in the notebook, but this means that I want to start my chain. I need to tell the chain where to start from. So I'm actually starting it from the true values. Okay, that's obviously cheating, because if I know the true values, why am I trying to do the inference? But let's just see what happens when we do that. And then I make, this is a joint plot that's using the Seaborn library. It has this nice joint plot thing, which will show you simultaneously the two-dimensional distribution, and then it'll show you the one-dimensional projections. Okay, so in the language of probability, these are the marginalized distributions, and this is the fully joint distribution. Okay, so our parameters, the slope and the offset. So we get this cloud of points here. I could fit this to an ellipse, or I could calculate some numerical ellipse, which will be some 95% confidence level numerically. That'll be a little noisy. But this is the kind of result that we want when we do Bayesian inference for the scientific problems we're interested in. These points sample fully the posterior distribution. Okay, so I can look for the most probable point. I can get 68, 95% confidence levels. Really, what I recommend you do is, once you've gone to all this trouble, is you don't boil it down to some Gaussian summary statistic like the sigma. You actually put this type of plot in your paper. I mean, that's really, and you tabulate it and you make it available for other people to download, so they can combine. They can use your results as a prior for their own analysis. Okay, so I cheated here and used the true values for starting the Markov chain. But let's try instead of starting at m true, let's just offset it. So we're going to start it at something which we know is not the true answer. Okay, in this case here, I mean, the plot looks basically identical, but we can use samples is a pandas data frame, and the first thing, if someone just hands you a random pandas data frame, first thing you should always do on it is call the describe method, which will just print out some summary statistics, kind of get a handle, so you can see what are the columns, what are the features in that data frame, but also the summary statistics. So if you look at this, you see that the differences are at the sub-percent level. So it's saying that the Gaussian statistics for this distribution really are essentially no different. We know that the first point is different, right? We shifted the first point by 0.1, so that's one grid square. So it definitely starts out at a different place, but it very quickly gets to the equilibrium, and it's sampling essentially the same distribution. So you're not getting identical results, but they're indistinguishable. So it doesn't. You don't need to know the true answer in order to initialize your chains. Okay, generally you don't want to assume a flat prior. So let's say that our prior belief is that the slope has to be somewhere between 0.4 and 0.7. So we can put a prior on that. Okay, so the way we do that is we say just top hat, right? Everyone has a top hat right at home. So your top hat is just a uniform distribution that's clipped, so it's equally likely to be between 0.4 and 0.7, but definitely not anything below or above that. I'm still leaving a flat prior on my offset. So when I feed that, so that's just going into basically you had the log likelihood, and now we add to it the log prior, which is just going to be constant in this range and minus infinity outside of that range. And when we feed that into the Markov chain sampler, this is the chain we get out. Okay, so notice how it's clipped. It never goes beyond below 0.4 or 0.7. The distribution I showed you before with flat prior was basically Gaussian. We could have gotten the same answer for the line fit just using Gaussian approximations for everything. There wouldn't be any need for sampling. But at this point here, this is a very non-Gaussian thing, okay, because it has these hard edges in one direction and soft edges in the other direction. But that's no problem, since this is really just a numerical sampling approach. It has no problem with with this non-Gaussian, not really even continuous output distribution. So now we've sampled the posterior with that interesting prior. We can also put a prior on let's say that someone's already measured the offset. Okay, so really the thing that we're contributing is we're measuring the slope, but someone's already measured the offset. In fact, they did a much better job than we're able to do with our data. Okay, so they measured that it was minus 0.2 with an uncertainty of just 0.02, so just a 10% uncertainty. So I can feed that in. So that's a Gaussian prior. So we have a top hat prior on the slope and a Gaussian prior on B. When I feed that into my chain generator, then these are the samples that come out. And so now, if we look at the projection for B, we're basically just getting out what we put in. Okay, so that's saying that we're really not contributing anything to the knowledge of the B parameter because we had such a strong prior. But that doesn't matter because it still lets us optimally learn about the other parameter that we're interested in here. Okay, so it's just an example to show that once you have this this black box MCMC, you just need to write down the log likelihood, and then you specify your priors, and then you can generate a sample that solves the Bayesian inference problem. Okay, so I'm just going to finish up for today with just some practical advice for using Markov chain Monte Carlo. So it's quite tempting to assume that the samples that we get out of these fancy chain generators have properties that go far beyond what the actual guarantees are. But it's important to avoid that temptation. So remember that the samples are only guaranteed to sample the distribution you care about, the posterior for a Bayesian problem, after some unknown number of samples. Okay, so you hear people talking about burn-in. So the idea of burn-in is that I'm just going to throw away the first B samples just to make sure that I've run it long enough that I've got to equilibrium. But how long should that be? Well, you really don't know. There's no rigorous way to know how much data you should throw away. So I don't think everyone would agree with this, but my take on this is that you just have to accept that the start of your chain for some unknown length is going to depend on what the initial value is. And so in general, I don't advocate throwing away any burn-in. Instead, what you need to do is you need to make sure that you start from a point that is probable. Okay, so if you start from some point that's just way outside of your target distribution, if your target distribution looks like that, if you start with some point out here, then for sure the initial points in your chain are going to be walking over to it. And you don't want to have those. Those are very unlikely points. But it's because you started from somewhere that's unlikely. Okay, so I think the right way to do Markov chain Monte Carlo is to start with something that's at a reasonable probability. It doesn't have to be right at the peak. It can be out here, but it should be something that has a reasonable probability. If you're going to make a chain with 10,000 elements, it just needs to be probable at the 1 in 10,000 level. Okay, and so that, what type of problem is that? That's an optimization problem. Right? That's remember the Laplace method. You can just run an optimizer to make sure. With an optimizer, you can actually find right what the peak of the distribution is. Okay, so it's important that you don't just feed in. If you really have no idea what the distribution looks like, you have to first run an optimizer and pick a reasonably probable point. And once you've done that, then you don't need any burn-in. Okay, but if you just say, well, I'm going to arbitrarily throw away the first 1,000 points, you're kidding yourself because you have no idea whether those 1,000 points, whether you've cut away enough if you don't know that you started somewhere probable. Okay, so the other issue is, remember those repeats that we get? So repeats are very non-random, and in general, there's no guarantee about, if you take two numbers from the chain that are separated by some distance, m, you don't really have any guarantees about their correlations. And so another approach you hear people talking about is thinning. So I'm going to take only every fourth sample, and I'll throw away the others. And hopefully that's going to get rid of the repeats. Okay? But there's nothing wrong with the repeats. Okay? The repeats are actually essential to get the correct weight of every sample. And as long as you always treat them as weights and propagate those weights through, you'll still get the right answer. Okay, so you can calculate, you can use your Markov chain to calculate statistics marginalized, means, whatever modes, as long as you use the weights properly. And you never need to assume that adjacent points are independent of each other. So again, thinning I don't think is a good idea, right? You've spent a lot of time and effort to generate these chains. Why do you want to throw away out 3/4 of the work? So. Okay, then finally, how long should your chain be? So there are some empirical methods to give you a handle of whether your chain is long enough. So one kind of that's fairly intuitive is the autocorrelation. So once you've run your chain for a while, you can just do some numerical experiments on it. You can calculate the mean and the sigma of your chain, and then you can, for example, calculate this autocorrelation. So this as a function of k. So you just say how correlated are points that are 10 apart on the chain or 100 apart on the chain. And you just find out how far apart they need to be until this autocorrelation gets close enough to 0 to the level that you're comfortable with. So that'll tell you the correlation length of your chain. And then make your whole chain 10 or 100 times longer than that. Okay, so that's kind of just a rule of thumb for getting a chain where you don't really need to worry about that avoids the problem. Remember the second example in filling the square where you had that worm that really hadn't gone anywhere. So that if you use that approach, that would tell you that you need to go much longer in order to fill out the square. For the specific example of Gibbs samplers, there's another metric, this Gelman and Rubin thing, which is probably the most popular approach. So which update rule should you use? Remember I told you there's a family. There's the Gibbs, Metropolis, Hastings. But then there's those special cases like Gibbs and Metropolis and Hamiltonian. So the way to figure out which of those update rules you should use is to answer some questions. So if one of those special cases is appropriate, the way to determine that. So first of all, can you efficiently sample from a complete set of conditional distributions? So what that means is, let's say you've got, if you have you're in a 3-parameter space, A, B, C. So if you can sample from if you can pick an A when B and C are fixed, and you can pick a B when A and C are fixed, and you can pick a C when A and B are fixed. That's what I mean by that. You have 3 conditional distributions. If you can write down code that will sample from all 3 of those things, then you can use Gibbs sampling. Okay, and when you can do that, you always should, because Gibbs sampling is going to be a lot more efficient. The really nice thing about Gibbs sampling is that there's never any repeats, okay, except just accidentally.
Does that information go in the likelihood function?
Well, so you would need to be able to write down. So normally with Metropolis Hastings, you're going to have your proposal, and you need to be able to just sample from that proposal, like a multivariate Gaussian. But here, you're going to have to be able to have a piece of code for every parameter, right? If you have 3, you'd have to write something that will generate a sample of A, given a B and C, B given C, A and C. So So you'll need to write 3 pieces you have to provide 3 samplers, yeah. So generally you have to do a bit of work, but both on paper and then encoding. But then it will be a lot more efficient. So the other special case is, can you compute all the partial derivatives of your probability density? So your P tilde. Let's say it depends on A, B, and C. So can you calculate the full partial derivative of that probability density with respect to A, and B, and C? And generally you can't. But if you can, then there's this other approach, Hamiltonian Markov chains, which will be a lot more efficient. Because basically what it uses is a physics analogy. Your chain is now kind of is modeled as a particle in some multi-dimensional space, and it's actually going to be following Hamilton's. It's going to be moving under Hamilton's equations. So you actually construct a potential energy that mirrors the probability density that you're trying to describe. And statistical mechanics guarantees that that particle moving in this kind of abstract space will sample your distribution. So it's a lot more efficient, but it requires that you can calculate the partial derivatives, basically the momentum of your particle. So there is no best algorithm, and you should generally just will need to benchmark your problem against the the different methods. And also, although I showed you on one page how to implement Metropolis Hastings, and it's fun to do that, and it's instructive. In general, you shouldn't do that because there's a lot of kind of subtleties to getting this right and getting it efficient. So, for serious work, you should let someone else do the hard work, and that means using existing package. So finally, which package should you use? So this is just my kind of personal perspective. I think for initial exploratory work, you should always start with this package here called MC. And what that does is implement something called ensemble sampling, which I didn't talk about, but it follows the idea you were mentioning, and that's to have multiple walkers. So that's kind of here you might have 100 walkers, so they're simultaneously crawling around your target space. But the real idea, the key idea behind MC is that it's constructed in a way that's affine invariant, which means that if you're trying to sample from a probability distribution that looks like that, which seems like it would be really inefficient to sample from because you'd always be jumping out of the distribution and then getting stuck at the same point. If there's some affine or linear transformation that lets you squash it into something that's rounder, it basically samples in an affine invariant way. So it will sample this just as efficiently as if it was this. So that's, for a certain class of kind of stretched, where you've chosen parameters that make your probability density look really stretched out. If there's a linear transformation of those that would make it rounder, you get the same efficiency. If you're going to use Hamiltonian Monte Carlo, remember you need to have those partial derivatives, but you don't actually have to be able to calculate them analytically. You can do them numerically, or even better is you can have if you write down your probability density in a way that can be automatically differentiated. So it's basically analytic differentiation, but it's you're not doing you're letting the code, basically using the inspection of the code structure to, like if you write your probability density and it has a sign in it, well, I know that the derivative of sine is cosine, right? So the fact that I've written down a sign in my code means that I can analytically calculate the transformation. I know that cosine is its derivative. And that's one of the main innovations behind these tensor computing packages like TensorFlow or PyTorch. Okay, they force you to write down your probability density in their own language, so you can't use math in Python. You can't use the math cosine or even the NumPy cosine. You have to use the TensorFlow cosine or the PyTorch cosine. But once you've done that, everything can be automatically differentiated. And it's not numerical. It's really analytic derivatives, or what are more technically called automatic derivatives. So there's both. So those are really good frameworks for doing Hamiltonian Monte Carlo. In fact, there's that ecosystem is now pretty rich. So there's this thing called Edward, based on TensorFlow, and Pyro, which is based on PyTorch, which they have built into them the code to handle all of calculating these derivatives and do this Hamiltonian Monte Carlo. They also do the variational inference technique that we'll be talking about tomorrow morning. So the last thing, don't get stuck in the idea that this is the only way to do Bayesian inference. So there's a whole nother approach, which with very different trade-offs, and that's variational inference. So I'm going to stop here now so we can get lunch, but then I'll start tomorrow by talking about this other approach, variational inference. Okay. And I'll be around for the rest of the week if you have any questions about this, and I'll also send X the link to the GitHub repo so you can download the notebook and play with it yourself. So.